So now we're going to do some calculations using equilibrium constants. The equilibrium constants do depend on the temperature. So you'll often see the temperature being specified, but it's not actually part of the equilibrium expression. Usually you can look these things up in tables in books or on the internet, and it'll say this is the equilibrium constant at, and it'll give the temperature. A lot of times that's 25 degrees Celsius because that's sort of room temperature, but some reactions only occur at other temperatures. And so they put it in there so that you know what temperature they were measuring at, but it doesn't actually get included in the calculation. The concentrations are always in moles per liter, which is not, we're going to talk about that I think in chapter 12, but it's the number of moles in 1 liter volume of whatever that is. And for now, we don't really need to know too much about this. The units are not going to cancel themselves out beautifully. And so what we do is we do all of our concentrations in moles per liter, and then we drop the units for the equilibrium constant, because otherwise they would end up being all kinds of weird units. And so we just decided we're not going to mess with units on KEQ. At a given temperature, the equilibrium constant is always going to be the same, but the concentrations of reactants and products may be different. They will be related to each other through the equilibrium expression. So let's look at how we might do this. So here's a reaction, chemical equation, hydrogen plus iodine in equilibrium with 2 hydrogen iodides. This is a gas, so it's not named as an acid. And here they're giving us the concentration of hydrogen, the concentration of iodine, the concentration of hydrogen iodide. This capital M is an abbreviation for moles per liter. So that means 0.11 moles per liter. So the units are fine, and I'm not going to try to trick you with units in here. I'm going to use the units because that's what we need to do, but we're not going to be tricking each other with units. Okay, so those are all moles per liter, the appropriate unit. And they're asking us to find KEQ. So the first thing we do is we write the equilibrium expression, and then we take these numbers and we put them in. So HI is 0.78, so I'm going to put that in here, and that's squared. And down here I have 0.11 and 0.11. And then I just do the math, and I come up with a number, and we're going to ignore units. Okay, you've probably been waiting all semester for me to say, we're going to ignore units today. Don't ignore units for other things, just for equilibrium constants. Any questions? So let's do one. Here's a reaction of carbon monoxide and hydrogen gas. It's allowed to come to equilibrium at 225 degrees Celsius. The measured equilibrium concentrations are, and they give them to us here, CO is 0.489, H2 is 0.146, and CH3OH is 0.151. What is the value of the equilibrium constant at this temperature? So we need to write the equilibrium expression and then take the numbers and put them into it and calculate it. So KEQ equals, it's the products over the reactants. So the product is CH3OH, and the reactants are CO and H2, and H2 is squared because it has a coefficient of 2. And now I'm just going to take the numbers and plug them in. So CH3OH is 0.151, and that's divided by the concentration of CO, 0.489, times the concentration of H2, 0.146, and that's squared. Now be careful when you talk to your calculator. This is how I'm going to do it. 0.151 divided by 0.489 divided by 0.146. I'm going to press the x squared button, and I'm going to press equals. And I come up with KEQ being equal to 14.5. No units. Any questions? Can you get your calculator to do that? You have to remember that things that are in the denominator are divided, and that this number has to be squared. Anybody need me to speak to their calculator? No? Okay. I'm having problems with my buttons today. Maybe that's because my kids pushed too many of them over the weekend. Using equilibrium constants in calculations. So we just learned how to calculate an equilibrium constant given concentrations. But if we're given the equilibrium constant and all but one of the concentrations, we can find the missing concentration. So here's another chemical equation, and the equilibrium constant is given, and they're giving us two of these concentrations, and they're asking us to find the other one, CO2. So again, we're going to start out by writing the expression for the equilibrium constant. So it's the products divided by the reactants. And now we're trying to solve for CO2. So this becomes a matter of algebra. So I'm going to rearrange this equation to solve for CO2. You end up with CO2 equals KEQ times COF2 squared divided by CF4. I encourage you to rearrange the equation first and then stick the numbers in. So we're going to plug the numbers in, and we're going to come up with the concentration. And now the unit, moles per liter, is going to magically reappear. There were no units on KEQ, but we understand by convention that all of the concentrations are in units of moles per liter. So let's do an example. Diatomic iodine decomposes at high temperature to form iodine atoms according to this reaction. And here's KEQ is 0.011 at 120 degrees Celsius. Is that a big number or a small number? That's a small number. It's not super small, right? But it's smallish. It's definitely less than 1. So what do we think is going to happen? Are we going to have more product or more reactant? More reactant, because the numerator is going to be smaller. So that's just kind of a thinking about it. In an equilibrium mixture, the concentration of iodine is 0.1. What's the concentration of I? So KEQ is going to equal the concentration of I squared divided by the concentration of I2. Now we are trying to find the concentration of I. Right? So what I'm going to do is I need to get rid of this guy. So I'm going to multiply, well actually, let's do the cross multiplying thing. Let's just stick with what we've been doing. We'll cross multiply first because we have fractions there, and I know a lot of you are not exactly friends with fractions, and that's okay. No one says you have to be friends with fractions. Because what have they ever done for you anyway, right? So I cross-multiplied. I took KEQ times I2. And down here is a 1 that's not written, times I squared. And so I've got I squared on this side. Now what do I do here? I've got I squared. How do I undo the square? Square root. So I need to take the square root of both sides. I'm going to take the square root of this and the square root of that. And the square root of something squared is just the something, right? Because 2 squared equals 4. And the square root of 4 is 2. Okay, square root and square are opposites of each other. So the concentration of I equals KEQ times the concentration of I2, and the whole thing is under the square root symbol. So KEQ is 0.011 and I2 is 0.10. I'm going to multiply those and take the square root. So on your calculator, 0.011 times 0.1, press the equals sign so that it finishes that, and then I'm going to press the square root button. Now some of your calculators may work a little differently, but that's how the TI-30XA works. 0.033 moles per liter, or 0.033 capital M. Any questions? Were we right in our prediction that the amount of product was less than the amount of reactants? There's 0.1 moles per liter of this and only 0.033 moles per liter of that. And so that agrees with this equilibrium constant being relatively small. We expect the reactants to be favored. Any questions?